So you may need to solve trig equations involving sec, cosec or cot. And these are really easy. It's basically the stuff you've done before, but with a little bit of work at the start. So here's an example where we need to solve the equation cosec x is equal to 2 like this. Now a reminder that cosec x is equal to 1 over sin x. We talked about this in the previous video. So therefore we can replace cosec x with 1 over sin x to make this 1 over sin x is equal to 2. And then what we can do is we can put this 1 over fraction here onto this side. So on this side it just becomes sin x, and on this side it becomes 1 over 2, so it's going to become half. And this is a trigonometric equation that we are very familiar with, of how we know to solve before from year 1 and from the radians chapter. So go back to those videos such as the simple trigonometric equations in year 1 if you don't know how to do this. But basically the way that we solve this equation is, firstly we need to do the inverse sin of a half, which if you put into a calculator we need to work in degrees. So if you put into a calculator it's equal to 30 degrees. And then we need to draw a quick pair of axes, and then we need to sketch a sin graph, which we've done here. And then we say that half is about here, let's say. Let's say half is about here. And we can see between 0 and 360 degrees, as we've drawn, there are 2 points at which the graph is equal to half. This point here, which we already know, is 30 degrees. And again, go back to the simple trigonometric equations part 1 video if you need a reminder of how this works. Because trigonometric graphs are symmetric, we know that the distance between this point 30 degrees and this point 0 degrees is going to be 30, and therefore the distance between 180 degrees and this point here is also going to be 30 like this. So therefore this point here is going to be this 180 degrees. So this 180 minus the difference to get to this point, so minus 30, and this is equal to 150. So this is this point here, 150. So therefore x is equal to, the two solutions are 30 degrees and 150 degrees. So as you can see, this question is basically stuff that we've covered before. The only difference is you just need to get it into this format here that's very easy to solve, and all you just have to do is sub in what cosec x is. So here's another example where we need to solve the equation 3 cot of 2 theta is equal to minus 5 in this interval here. Now because we've got these pi's in the interval here, this shows that we need to give our answer in radians. I talked about this in the previous chapter, trigonometric equations involving radians, so go back to that video if you need to. But what we basically need to do is, because we've got this 2 theta, we've got this inside the function transformation, we need to change this interval. At the moment it's in terms of theta, and we need to make it in terms of 2 theta, like this. So what this is going to be is we need to times everything by 2. So this is going to become 2 theta, and then pi times 2 is equal to 2 pi, and then minus pi times 2 is equal to minus 2 pi. So we switch the interval from in terms of theta to in terms of 2 theta, like it is in the question. And now we need to solve this equation here. So it's 3 cot of 2 theta is equal to minus 5. Divide both sides by 3 to get cot of 2 theta is equal to minus 5 over 3. And in the previous video we talked about that cot x is equal to tan x over or under 1, like this. So therefore we can rewrite this as 1 over tan of 2 theta is equal to minus 5 over 3, and we can move this 1 numerator onto the other side, so this becomes tan of 2 theta is equal to 1 divided by minus 5 over 3, and therefore this will become tan of 2 theta is equal to, so flip this fraction here to 1 times minus 3 over 5, so it's going to be equal to minus 3 over 5. Just a bit of a note, whenever we have this 1 numerator here and we move it onto the other side to make tan 2 theta here, all this will always do is just flip this fraction here, so it's minus 3 over 5, like this. And then what we're going to do, we're going to do the inverse tan of minus 3 over 5, which if you put into a calculator is equal to minus 0.540. So now I've just drawn a quick tan graph in this interval here in terms of 2 theta. The graph is just for our kind of working out the answers. It doesn't need to be a work of art of anything. They're not really going to mark us for it. It's just for our benefit. And we'll say that minus 3 over 5, we'll say that this is about here, for example, is this minus 3 over 5. And we can see there are 4 solutions. So we already know this one here. This one is the one that our calculator gave us. Make sure your calculator is in the radians mode. We talked about this in the radians basics video because we need our answer to be in radians. This was minus 0.54. So therefore the difference between this and 0 is 0.54, and we can use this because the graph is symmetric to figure out the other values. So this value here, the difference here, is also going to be 0.54, so therefore this value is going to be minus pi here minus the difference to get to this point, which is 0.54, which if you put into a calculator is equal to minus 3.68, and then this value here is going to be pi minus the difference here, which is 0.54, and if you put this into a calculator, this is equal to 2.60, and then this value here is going to be 2 pi minus, and then difference here is also 0.54. And if you put this into a calculator, you get out a value of 5.74. So therefore the solutions in terms of 2 theta are equal to this here, which is minus 0.54 minus 3.68, 2.60 and 5.74. So these are our solutions, but they're in terms of 2 theta, but we need them in terms of theta. So what we just need to do is we need to divide everything by 2. We need to divide everything by 2. So minus 0.54 is going to be equal to minus 0.27. Minus 3.68 divided by 2 is equal to minus 1.84. 2.60 divided by 2 is equal to 1.30. And 5.74 divided by 2 is equal to 2.87. So theta, these are the final answers. Theta is equal to minus 0.27, minus 1.84, 1.30 and 2.87. Now I've talked about this before with trig equations. There's a really good way in my opinion to check your answers in an exam to see if you've got the correct answers. If you sub in the theta values that you've got back into this equation here, you should get a value that's very close to minus 5. So let me show you what I mean by this with 1.30. I'm going to sub 1.30 back into 3 cot of 2 theta here. Now there's no actual cot function on your calculator, so instead we're going to write it as 1 over tan x, but it means the exact same thing. So this is going to be equal to 3 over tan, instead of 3 cot, it's going to be 3 over tan. And then we've got 2, and then we've got theta, and this is 1.30 in this instance. And if you sub this into your calculator, make sure your calculator is in the radians mode, you get a value of minus 4.99, which is very, very close to minus 5. Remember that for this equation, this question, what we're actually trying to do is we're trying to make both sides equal to each other. So we're trying to make 3 cot of 2 theta equal to minus 5. So for our values of theta, so for 1.30, if we sub in the 1.30 as theta and we get out an answer that is approximately equal to minus 5, this shows that this answer is correct. We're not going to get out exactly minus 5 because we've rounded it to 2 decimal places. We need it to be the exact answer to get out exactly minus 5. But if we get an answer that is approximately equal to minus 5, we know that we have got the correct answer, and you can do this for every single one of your solutions. If you have no idea what I'm talking about with this, go back to my trigonometric equations involving radians video for a bit more info if you have no idea what I'm talking about. So we've gone through equations. The other type of question they could ask you in this chapter is identities, when we've got these symbols here. And for these, you need to go from one side to the other. You can start whatever side you like, although it's probably best to always start with the side that's got more stuff on it, because it's always easier to simplify. So there's a couple of tips for questions like these. Firstly, you should always rewrite them in terms of sin and cos rather than sec, cosec, and tan x, stuff like that, using whatever they are equivalent to in sin and cos, because then it's easier to cancel stuff down. We'll see this in the sec. And the other thing is, if you've got two separate fractions or just two separate terms in general, you should always try and combine them by making the denominators the same and then combining them into one fraction. You normally find by doing that you can do a lot of simplifying down and it will get you to the other side. Just also, sin squared x plus cos squared x is equivalent to 1 comes up a lot in these questions. You'll often find yourself seeing this, and therefore you know you can just simplify this to 1, and therefore you can also see the equivalent cos squared x and sin squared x terms as well, so you can simplify things to those as well if you need to. So for question 1, we need to prove that sec x cosec x minus tan of x is equivalent to cot of x, like this. So remember the first tip, we should always write everything in terms of sin x and cos of x. So sec of x is equal to 1 over cos x, like this, and this is times cosec x, which is equal to 1 over sin of x minus tan of x, which is equal to sin x over cos of x. Okay, well, we can simplify this here. This is going to become sin x cos of x times the denominators together. This is over 1 minus sin x cos of x, like this here. And then what we're going to do, remember the second tip, is that if you have two fractions, you should always combine them into one fraction by making the denominators the same and then adding the numerators. And what we can do is this sin x cos of x, we can times this by sin x over sin x. Remember, sin x over sin x cancels down to 1, so all we're doing is timesing it by 1, so we haven't changed the value of the fraction. But what we can do with this is going to be equal to, so this fraction is still going to be the same, it's still going to be sin x cos x over 1, like this, minus, and then this here is now going to be sin x cos x, and this is going to be over sin x times sin x, which is equal to sin squared x. And now the denominators are the same, so now we can add these two fractions together, so this is going to become 1 minus sin squared x over sin x cos x. And remember that 1 minus sin squared x is equivalent to cos squared x, so therefore we can rewrite this as cos squared x over sin x cos of x. And then this is equivalent to, so we can cancel out the cos of x down here and one of the cos x down here, so this squared goes away, so this just becomes cos x over sin of x, like this, and this is equivalent to cot of x. So therefore we have proved that sec x cosec x minus tan of x is equivalent to cos of x. So for the second identity, we need to prove that this is equivalent to this. So we're going to start with this side here. Now, as we've got quite a bulky fraction here, what we're going to do, we're going to focus individually on the numerator and denominator first. So let's start by focusing on the numerator up here, which is equal to cot x times cosec x, like this. So this is equivalent to, so cot x is equal to cos x over sin x, and this is times by cosec x, which is sin x over 1, like this. So this is equivalent to cos x over sin squared x, like this. And then for the denominator here, this is a bit more complicated. So the denominator is sec squared x plus cosec squared of x, which we can write as cos squared x under 1 plus sin squared x under 1 like this. Now remember the tip of when you have two fractions, you want to combine them together to make one fraction. So what we're going to do is we're going to multiply this thing by sin squared x over sin squared x, so it becomes sin squared x over cos squared x sin squared x like this, and this is going to be plus, and then we're going to multiply this by cos squared x over cos squared x, so this becomes cos squared x over cos squared x sin squared x. And what we can then do is, because the denominators are the same, we can combine these two fractions, so it becomes sin squared x plus cos squared x over cos squared x sin squared x. And this is equivalent to, because sin squared x plus cos squared x is equivalent to 1. Remember, this comes up a lot, so you should always look out for it. Therefore, this is equal to cos squared x sin squared x under 1, like this. So therefore, the numerator is this, so it's cos x over sin squared x, and then this is divided by the denominator, which is this here. So it's divided by cos squared x sin squared x over 1 like this, which we can write as cos x over sin squared x times by cos squared x sin squared x over 1 like this, which is equivalent to, so cos x multiplied by this is going to be cos cubed x sin squared x over sin squared x times 1, which is still sin squared x. And then these two cancel out, so we're just left with cos cubed of x, which is required. We talked about in year 1 the identity sin squared x plus cos of squared x is equivalent to 1. Go back to the year 1 trigonometric identities video if you don't know what I'm talking about. So in year 2 there are two new identities that you need to be aware of. 1 plus tan squared x is always equal to sec squared x, and 1 plus cot squared x is equivalent to cosec squared x. These aren't given to you in the formula booklet, so you'll have to remember them, which I think is a bit harsh personally. I think these are quite difficult formulas of functions that you've probably never met before this chapter, and with these you normally rearrange them in order to sub one of the functions out for another one. The same for how we do it for sin squared x plus cos squared of x equal to 1. We're always subbing out either sin squared of x or cos squared of x. So look out for these 4 squared functions like this, and if you need to, you can sub them out for the other one in their individual equations if you need to. You could be asked to prove these identities, so let's start with 1 plus tan squared x is equal to sec squared x like this, and let's start with what we already know, that sin squared x plus cos squared x is equivalent to 1 like this, and then let's divide everything by cos squared x. So this is going to become sin squared x divided by cos squared x plus cos squared x divided by cos squared x, and this is equivalent to 1 over cos squared x. So as tan x is equal to sin x over cos x, therefore this is going to be equal to tan squared x. Cos squared x over cos squared x is just equal to 1, and as sec x is equal to cos x over 1, therefore 1 over cos squared x is equal to sec squared x, and therefore we have proved the identity that 1 plus tan squared x is equal to sec squared x. And then to prove the other identity that 1 plus cot squared x is equal to cosec squared x, it's basically the same. We start with sin squared x plus cos squared x is equivalent to 1, and then we divide everything by sin squared x this time. So this is going to be sin squared x over sin squared x plus cos squared x over sin squared x, and this is equivalent to 1 over sin squared x, like this. Sin squared x over sin squared x is obviously just equal to 1, and as cot x is equal to cos x over sin x, this here is equal to cot squared x, and this is equivalent to, and as cosec x is equal to 1 over sin x, therefore this here is equal to cosec squared x. And we've proved the identity that 1 plus cot squared x is equivalent to cosec x, which is required. Now, I said before that remembering these formulas is quite difficult because they're quite complicated and it's still quite unfamiliar trigonometric functions. The way that I remember it is if I'm doing a question I realise that I might need one of the two identities that I showed, I normally start with this and then just do this very quick proof to remember which one goes where. I think it's very easy to maybe just get these two mixed up, for example, and then therefore you'd actually end up with the wrong formula. So I think maybe that's the best way to do it. If you're in an exam and you realise that you probably need one of the two identities, start with this, quickly do this proof, and look at the formulas that you get out of it. So the rest of this video is dedicated to past paper questions. So here's an example where we need to solve the equation cosec squared of 2x minus cot 2x is equal to 1. So this is worth 7 marks. It looks like a pretty horrible equation, so let's just take it slowly. So we have these two x's present inside the function, so we're going to need to change this interval here. At the moment it's terms of x, so we need to make it in terms of 2x, so we need to times everything by 2. The 0 is going to be times by 2, so this will still be 0 degrees, and the 180 needs to be times by 2 to get to 360 degrees, like this. So this is the new interval. Okay, so this equation here, this is a quadratic trigonometric equation. Now, we talked about how to solve these in the harder trigonometric equations part 2 video in year 1. I highly suggest going back to that video if you struggle with these. The first key with this is the only way that we can begin to solve this is if we have one trigonometric function present. The problem at the moment is we've got two. We've got cosec and we've got cot. We can solve this if we have only one of these present, but as we've got two, we can't solve it yet. And the way that we get around this is by using the interval that we talked about before. 1 plus cot squared x is equivalent to cosec squared x. And what we can do is this cosec squared of 2x here, we can substitute this for 1 plus cot squared of 2x, so therefore cosec would go away and we would only be left with cot here, and then we can begin to solve this. Just a bit of a trick with these questions. You can see we have this cot 2x without the squared here. Whenever there is no squared part here, we can't use an identity like this. There is no way that we can get rid of this, and therefore this is telling us that the quadratic that we want to solve will have cot in it, because there's no way that we can get rid of this. But there is a squared next to the cosec, so that is telling us that we can get rid of the cosec and be left with cot. The indication is that there is no cosec 2x without like a squared here that we can't get rid of. There is only cosec squared which we can get rid of using the identities. So now let's sub out the cosec squared of 2x for this. So this is going to become 1 plus cot squared of 2x, and it's going to be minus cot of 2x, and this is equal to 1. And then we're going to make this side equal to 0, so it becomes a quadratic equation that we can solve. So it's going to be cot squared of 2x minus cot of 2x, and then this 1 is going to cancel out with this 1, so this is going to be equal to 0. And this is a quadratic equation. Now if you want to, you can make a substitution like y is equal to cot of 2x, for example, and then you can rewrite this as cot squared of 2x is y squared minus cot 2x is y, and this is equal to 0. And hopefully you can more easily see that this is a quadratic equation. If you want to, you can do the rest of this question in this format like this if you want to. I'm just going to do it in this format here. So what I'm going to do is we need to solve this quadratic equation. We need to factor out cot of 2x, so this is going to become cot of 2x like this. Cot squared of 2x is going to be cot of 2x, and then minus cot of 2x is going to be minus 1, and this is equal to 0. And therefore, there is going to be two solutions to this equation. Cot of 2x is equal to 0, and cot of 2x minus 1 is equal to 0, and move the minus 1 onto the other side to get the cot of 2x is equal to 1, like this. Now remember that cot x is equal to 1 over tan x, so therefore we can rewrite this, so we can write cot 2x is equal to 0 as 1 over tan 2x is equal to 0, and we can rewrite this as 1 over tan of 2x is equal to 1. And then what we can do, we can rearrange these, so we can move this one numerator onto the other side, so it becomes tan of 2x is equal to 1 over 0. Now of course we can't actually divide by 0, but the key to this is cot of 2x, or just cot of x in general, is equal to 0 when tan of x is an asymptote. This is kind of what this 1 divided by 0 is trying to say. So therefore a solution to this is when tan of 2x, we're not going to write it as 1 divided by 0. We can either say it's approaching infinity, or we can just say when it's an asymptote. A solution to this is when tan of 2 of x is an asymptote, and then this one we move the one numerator onto the other side, so it becomes tan of 2x is equal to 1 divided by 1, which is 1, like this. So now we have two equations. Tan of 2 of x when it's an asymptote, and tan of 2x is equal to 1 are the two solutions. So let's start with tan of 2 of x is an asymptote. So we've drawn a quick pair of axes in this interval here between 0 and 360 for the 2x interval, and we need to find when tan is an asymptote, and we can see that this is here and here. So this is 2x is equal to 90 degrees and 270 degrees. And now we need to solve the equation tan of 2x is equal to 1. So the inverse tan of 1, if you put it into your calculator, is equal to 45 degrees. So here's another tan graph in the interval 0 to 360, and we'll say 1 is about here. So we have two solutions. We already know this one is 45 degrees, and therefore we know the difference between this point and this point, between 0 and 45, is 45. So therefore the difference between 180 and this point is going to be 45 degrees. So therefore this point here is going to be 180 plus the 45 here, which is equal to 225 degrees. So 2x is equal to 45 degrees and 225 degrees. So therefore 2x is equal to 90 degrees, 270 degrees, 45 degrees, and 225 degrees. But this is 2x, we need x, so therefore we divide everything by 2, so x is equal to 45 degrees, 135 degrees, 22.5 degrees, and 112.5 degrees. And this is the final answers, that 45 degrees, 135 degrees, 22.5 degrees, and 112.5 degrees. Now, I acknowledge that this is a really complicated looking question, quite a lot of working. Just take it one step at a time, go through the steps gradually, and hopefully you'll be able to get the answer. So here's another past exam question. So for part I, we need to prove that this side is equivalent to this side. So this is an identity question. Now remember the two tips I said for identities. The first one is to write everything in terms of sin and cos, which is already done for us here. And the second tip is if you have two fractions, you should make the denominators the same and then combine the fractions into one by adding the numerators together when the denominators are the same. So that's what we're going to do here. So what we're going to do, we're going to times this fraction here by Cosecs over Cosecs. Remember that this is equal to 1 as the numerator and denominator is the same, so the fraction will still be the same, and we're going to times this fraction here by 1 plus sin x over 1 plus sin x. So therefore what's going to happen is the denominators are going to become the same. They're both going to become cos x of 1 plus sin x. So let's do this now. So this here is going to be cos x times cos x, which is equal to cos squared x, and this is over cos x 1 plus sin x, like this here, and then this is plus, and then 1 plus sin x times 1 plus sin x is equal to 1 plus sin x squared, and then this is over cos x 1 plus sin x, like this. And you can see now that the denominators are the same, so now we can combine the numerators. So this is equivalent to cos squared x plus 1 plus sin x squared, like this, and this is over cos x 1 plus sin x, like this. Okay, so 1 plus sin x squared is equivalent to 1 plus sin x multiplied by 1 plus sin x, like this, and this is equal to, so 1 times 1 is equal to 1, sin x times 1 is equal to sin x, but there's two of them, so it's going to be 2 sin x, plus, and then sin x times sin x is equal to sin squared x, like this. So we can rewrite this here as cos squared x plus, and then this expanded. I'm going to write it the other way round. So it's going to be sin squared x plus 2 sin x plus 1, and this is over the cos x 1 plus sin x, like this. Now for questions like this, you should always be looking out for the identity that sin squared x plus cos squared x is equivalent to 1 in some way, and see if you can somehow find this identity. And you can see that we have it here. We have cos squared x plus sin squared x, like this. So this here is equal to 1, and therefore it's going to be 1 plus 1, like this. So this is going to be equal to 2 plus 2 sin x, where this whole thing here is cancelled out as 1, and then this is over cos x 1 plus sin x, like this, and we can factor out the 2 up here, so this becomes 2 of 1 plus sin x over cos x of 1 plus sin x, like this, and then we can cancel out the 1 plus sin x, so this is equivalent to 2 over cos x, like this, and this is of course equivalent to 2 sec x, like this, which is required. So for the second part, we need to find between 0 and 2 pi the solutions to this equation here. Now, these two parts are always going to be linked in some way. They've got I and I, like this. And we can see that this here is the same as this. And as this is equivalent to this, therefore we can write this as 2 sec x. And this is equal to 4. Divide both sides by 2 to get that sec x is equal to 2, and remember that sec x is equal to 1 over cos x, so therefore this is going to be equal to 1 over cos x is equal to 2, so this is going to be that cos x is equal to a half, and therefore we're going to solve this equation here. So firstly we do the inverse cos of a half, which is equal to, if you put it into a calculator in radians, it's pi over 3. So then we just draw a quick pair of axes and a very quick cos graph like this, and then we say that half is about here, for example, and we can see that there are two solutions in this interval here. So this one here we already know is pi over 3, and therefore we can figure out the difference between pi over 3 and pi over 2. It's going to be, so it's going to be pi over 2 here minus the pi over 3 here, and if you put this into a calculator, this is equal to pi over 6. So the difference between pi over 3 and pi over 2 is pi over 6. So therefore the difference between 3 pi over 2 and this point here is also going to be pi over 6. So therefore this point here is equal to 3 pi over 2 plus the pi over 6 difference, which if you put into a calculator is equal to 5 pi over 3. So therefore the x solutions are pi over 3 and 5 pi over 3. And then that's the final answer. And again, you can check your answers to this question by subbing in your x values into this equation here. And if you put it into your calculator in radians mode, you should get out an answer of exactly 4. So here's a couple more past exam questions for you to have a go at. So pause the video, have a go, and I'll go through the answers in about 5 seconds. So for question 1, we need to solve between 0 and 360 degrees this equation here. And hopefully you realise that this is a quadratic because we have these powers to the 2 here. Now we've already tackled how to do a quadratic problem in this video. The first problem we have is we can only have one trigonometric function present, but the problem is we've got 2. We've got tan, but we've also got sec, so we need to get rid of one of these, and because we've got this sec theta without to the power of 2, there's nothing we can do about this, so therefore this will be there at the end. So we need to rearrange this in terms of sec theta, so we need to get rid of the tan theta, which we can do by using the identity that 1 plus tan squared of x is equivalent to sec squared of x. And moving the 1 onto the other side to get that tan squared x is equivalent to sec squared x minus 1, and then sub this in for tan squared theta, so it becomes 2, and then sub this in, so it becomes sec squared theta minus 1 plus 4 sec theta plus sec squared theta is equal to 2, and then expand the brackets so we get 2 sec squared theta minus 2. You can see we only have sec left now. Then it's plus 4 sec theta plus sec squared theta is equal to 2, and then move this 2 onto the other side, so therefore this side is equal to 0. So it's the quadratic equation that we're familiar with, where it's equal to 0. So this will become 2 sec squared theta plus sec squared theta is equal to 3 sec squared theta. Then it's plus 4 sec theta, and then it's going to be minus 2, and then this minus 2 comes across as well, so it's minus 2 like this, which is going to simplify to minus 4, and this is equal to 0. And this is a quadratic equation where we've got this sec squared theta and this sec theta here. If you want to, you can make a substitution like y is equal to sec theta and make this 3y squared plus 4y minus 4 is equal to 0, and then you can solve it in this format if you prefer it like this. I'm just going to solve it in this format here. So this is a quadratic equation we talked about in chapter 2 of year 1, all the ways that we can solve quadratic equations. We can factorize, we can use our calculator, we can use quadratic formula. I'm just going to factorize it, so it factorizes to sec theta plus 2 and then 3 sec theta minus 2, and then this is equal to 0. So therefore the two solutions are when sec theta plus 2 is equal to 0, so therefore this is going to be when sec theta is equal to minus 2, and when 3 sec theta minus 2 is equal to 0, so when 3 sec theta is equal to 2, so therefore when sec theta is equal to 2 over 3. And because sec theta is equal to 1 over cos theta, therefore we can rewrite both of these as 1 over cos theta is equal to minus 2, and this one is going to be 1 over cos theta is equal to 2 over 3, and therefore we can put these 1 numerators onto the other side. So this one is going to become cos theta is equal to minus a half, and this one is going to become cos theta is equal to 3 over 2. However, you should notice something immediately about this, hopefully, and that is that cos theta cannot be equal to 3 over 2, and this is because cos theta is always less than or equal to 1. It cannot be bigger than 1 cos theta. Remember how the graph looks, you cannot get a cos theta value that's bigger than 1, so therefore this can't be a solution, so therefore we can ignore all of this and just focus on this here. So this is cos theta is equal to minus a half, and we're just going to solve this. So firstly, let's take the inverse cos of minus a half, which if you put into a calculator, we want it in degrees, is equal to 120 degrees. So we draw a really quick cos graph, and minus a half we'll say is about here. We can see that there are two solutions. We know this one here is 120 degrees, which is the one the calculator gave us, and we can figure out that the difference between 120 degrees and 90 degrees is going to be 120 minus 90, which is equal to 30. So therefore the difference between this point and this point is 30. So therefore the difference between this point and 270 is also going to be 30. So therefore this point here is going to be the 270 minus the 30 difference to get to this point, which is equal to 240 degrees. So therefore the two solutions for theta are 120 degrees and 240 degrees. So for question 2 part A, we first need to show this identity here. So let's start with this side here. Now the two tips I said for identities, the first one is to rewrite this just in terms of sin and cos, and as cosec theta is equal to 1 over sin theta, we're therefore going to rewrite this as 1 over sin theta minus sin theta, like this. And then the second tip is to combine everything into one fraction if we have a fraction like this, which we do. So we're going to combine this into one fraction like this, and we're going to do this by multiplying sin theta by sin theta over sin theta, so therefore it has this denominator here, and this is equal to sin squared theta over sin theta. So this is equivalent to this, we've just multiplied it by 1 here, because remember this is equal to 1. So this is equivalent to 1 over sin theta minus sin squared theta over sin theta, which we can then combine the numerators. This becomes 1 minus sin squared theta over sin theta. And I said before, you should always be looking out for the identity that sin squared x plus cos squared x is equivalent to 1. And we have it here if we rearrange this to cos squared x is equivalent to 1 minus sin squared x. So whenever you see a sin squared x or a cos squared x or both added together, you should always be thinking of this identity, because we can rewrite this 1 minus sin squared theta as cos squared theta. So this is equivalent to cos squared theta over sin theta, like this, and we can rewrite this as, so we've got cos squared theta up here, so we can rewrite this as cos theta multiplied by cos theta over sin theta, like this, and hopefully you can see that these are equivalent, and therefore we can rewrite, remember that cos theta over sin theta is equal to cot theta. We can rewrite this as cos theta cot theta, which is required in the question. So again, for these identity questions, always write everything in terms of sin and cos, and then try and combine the fractions like this, and always look out for this sin squared x plus cos squared x is equivalent to 1. So for part B, I have to be honest, I think this is a really, really difficult question. I wasn't able to get it. I had to look at the mark scheme, and at certain points I had to keep rereading the mark scheme because I couldn't quite understand what it was saying. So if you got this, really, really well done. If you didn't get this, I wouldn't panic. I think the chances of you being asked a question this difficult are really, really low. So we need to solve between 0 and 180 degrees this equation here. Now because it's B and A, you probably think that it's going to have something to do with this. And they do look very, very similar because we've got this cosec theta minus sin theta, and it kind of looks like this, and we've got this cos cot here, which we've got here as well. This side here, we cannot use this identity because we need the two values to be the same inside the functions, but here they're different. So we cannot use this identity on this side in order to make any substitutions. But we can on this side here because the two values inside the functions are the same as they are up here as well. So we can sub here cosec x minus sin x for cos x cot x here. And because there doesn't really seem to be any way to figure out this here, let's make this substitution. So it's going to become cos of x, and then cot of x is equal to cos x and then cot of 3x minus 50, like this. Now here the mark scheme does something which I've never seen before. So you might be tempted to divide by cos x here, and I would have wanted to avoid that because I didn't think you could really divide by cos of x if cos x equal to 0 is a possible solution, and here it is, because cos x, if it was equal to 0 here, this whole thing would be 0, and if this is equal to 0, this whole thing would be 0. So both sides are equal to each other, they're both 0, so therefore cos x equal to 0 is a solution. And I normally thought that you can't divide by cos of x if this was the case. The way the mark scheme gets around this is it accepts that cos of x is equal to 0 is a solution, finds the values of x for when this is the case, and then divides by cos of x. And this does actually work. It is quite a clever way of getting around this. I'll explain a bit more in a sec why this does work. First of all, let's find the values, the solutions for when cos of x is equal to 0. So the inverse cos for 0 in degrees is equal to 90 degrees. And then between 0 and 180 degrees, there is only one point in which cos of x is equal to 0, which is 90 degrees. So therefore, the only solution for cos of x is equal to 0 is 90 degrees. And now what the mark scheme does is it divides both sides by cos of x to get cot of x is equal to cot of 3x minus 50. Now the reason I've always thought is that you shouldn't divide by cos of x if cos of x could be equal to 0 is because if you solve this you will get the correct solutions, but you will be missing this solution here when x is equal to 90 degrees. You'll be missing the solution when cos of x is equal to 0 if you divide by cos of x when cos of x could have been equal to 0. But the question kind of cleverly gets around this by saying that cos of x could be equal to 0, finding the solution for this, and therefore even though we will miss this solution by dividing by cos of x, we have separately found it and we can just include it in our final answer. So I've never seen it dealt for in this way, but it does make sense and therefore is a valid way of doing it. And now we can solve this equation here for the other solutions here. Now the mark scheme just directly solves it from this. I'm actually going to say, remember that cot x is equal to 1 over tan of x. We can instead write this as 1 over tan x is equal to tan of 3x minus 50 over 1, like this, and therefore we can get rid of the 1 numerator to just make tan of x is equal to tan of 3x minus 50. These two here are equivalent, and because we've got tan of something is equal to tan of something, what we can actually do is we can actually get rid of these tans here to just say that x is equal to 3x minus 50. You might not have seen this effect before, but basically if we're applying the exact same function to both things, we don't actually, the function doesn't really have an effect anymore because it has the same effect on both sides and we can ignore it. These two sides are still going to be equal if x is equal to 3x minus 50. It doesn't matter about the tan. This is just going to take the exact same effect on both sides and we can just actually ignore it. So we can just get that x is equal to 3x minus 50 like this, and then solve this equation here. So minus 3x on both sides to get minus 2x is equal to minus 50, and then divide both sides by minus 2 to get that x is equal to 25 degrees. So this is another solution. So this next part is the ridiculously difficult part that I was referring to. So seriously well done if you were able to get this. There is another solution to this equation here. There is not another solution to this, but there is another solution to tan of x is equal to tan 3x minus 50. And this is because tan values repeat themselves. So I tried to show this on this graph here. So let's just take this value here. It doesn't matter what value it is. It has the same effect for all values. And you can see that there are two values for when it is equal on the x-axis here, and these are separated by exactly 180 degrees. The tan graph has a periodicity of 180 degrees, and because of this there is another solution where x plus 180 is equal to 3x minus 50. This here is also a solution. The best way to explain this is by saying that the 3x minus 50 is this point here. So it is this point on the kind of x-axis here. And then this point, the x plus 180, is this point here. So it's kind of this point on the x-axis. Even though these give out different points on the x-axis, because we've specifically tanned these values, when you tan them, they give out the same y value, such as that tan of x plus 180 is equal to tan of 3x minus 50. When you tan these specifically, they give out the same value and they're both equal to each other. So therefore we can solve this. So minus 3x on both sides and minus 180 from both sides to get that minus 2x is equal to minus 230, and then divide both sides by minus 2 to get that x is equal to 115 degrees. So therefore there are three solutions to this equation. X is equal to 90 degrees when cos of x is equal to 0, x is equal to 25 degrees, and x is equal to 115 degrees.